Okay, so welcome back to the second lecture of today, and the second lecture of today is about field evaporation physics. Field evaporation physics. What do we mean by that? Field evaporation physics is the physical process of turning a solid material into individual ions. Which brings us to the very name of it. Just like atom probe, field evaporation is also a bit of a misleading nomenclature because it's not an evaporation process. Evaporation is a physically defined process. We are not actually looking at evaporation. What it actually is a phase transition. It's a phase transition from solid directly to plasma. So if you remember your basic physics course, you've got melting, which is going from solid to liquid. You've got solidification, which is from liquid to solid. You've got evaporation, which is from liquid to gas, or you've got sublimation, which is from solid to gas directly. And what we have here is going from solid to plasma directly. So it would be something like I think François Vaupiot called it ionosublimation. But it's not actually an evaporation process. It's sublimation of an ion, ionosublimation, or something like that. But it's been called field evaporation for a long time. We've also called the atom probe an atom probe without being a probe for a long time. So I guess we're going to stick to field evaporation physics. And the question for us now is, what physics are happening and how are they relevant for what we do later with all the analysis stuff that we use the atom probe for? Okay, so we're going to go through general field evaporation physics today. Then we're going to look into voltage pulsing, which is going to be rather short because a lot of what's relevant with voltage pulsing we are going to cover when we go to the instrumentation after lunch. And then we're going to go to some introduction to what happens when we do laser pulsing as it stands early 2022. So everything is thermal. Okay, and with the general field evaporation physics, we will start looking at the so-called Imagehump model, which is a very simplistic view on what happens during field evaporation. It's horribly reproducing what's actually happening, but it's been very successful since the 50s, so we'll stick to it, and we don't have anything better, at least not for a fundamentals lecture right now. But we're only starting to apply quantum mechanics to the field evaporation process. Our colleagues at Max Planck in Düsseldorf have been doing that very successfully. So for now, we'll have to stick with the Imagehump model. We'll look at post-ionization. Then we will look at what happens at insulators. We'll look at field-induced stress. This is very, very important for our specimen yield. Then we'll look at the various imaging artifacts, as we call them. They're just physics of what happens there, but we need to understand where local magnification comes from, where chromatic aberration comes from, and where preferential retention comes from. And with that, let's just jump in and go straight into the Imagehump model. And let me just draw that for you, and let me just build it up slowly so that you can have a bit of an overview of what's happening there. And so essentially, the sketch that you just saw was the question of what actually happens if I have... No, why is it green? I don't want green. I want black. There's the question of what happens if I have a solid, and our theory actually doesn't even contain any information about what this is made up apart from the basics of quantum physics, but it's going to be made of some kind of atoms, but this is our solid. This is our solid here, and we have an atom, and the atom, we're gonna give the atom a little bit of color. And we're gonna have an atom that sits here, and we're gonna have a distance coordinate x. And our atom sits at a certain distance coordinate, yeah? And this is our x0. Yeah? This is where it sits happily. You know, it's just at, you know, at equilibrium, sits there, does nothing, has no field, no nothing. But eventually it moves to be an ion, yeah? An ion that is n plus charged. Yeah? That is n plus charged. And what we are looking into is how it goes from here to here. Yeah? How does this process happen? Yeah? What we're not looking at is, you know, what would happen if there's some steps here, if there are more atoms sitting here, or, you know, or more complex situation. And this is just the basic look we're talking. You know, and what's actually happening here is still much more than what we're talking about here. And we're doing that from an energetic point of view. Yeah? So we've got some energetic point of view. So we can now draw an axis where we are plotting our potential, some kind of potential of our atom in dependence of our coordinate x. And we will take the energy of the atom in free space. Still thought I had the line. In free space, this is our zero potential. Yeah? We'll just arbitrarily set that as, doesn't even need to be zero. I mean, we're not putting numbers in, so it doesn't matter anyway. So this is the potential of the free atom. This is the potential that the atom will have when it's free. And I think a lot of you have seen in your physics classes that an interatomic potential might look something like this, and then it asymptotically moves towards UF. Yeah? And obviously, so this is where our red atom sits. Yeah? So our red atom sits right here at this potential. And it's just happily living there and just thermally vibrating a little bit to the left and the right. But that's about all it does. And so what happens if I put a field on top of that? Well, nothing, or not much, because the atom is neutral, so the field's not going to affect it very much. I mean, it's going to polarize, yeah, but it's not going to have, it doesn't have a permanent dipole, so, you know, unless it's water, then it would, but yeah, it's not going to have, it's not going to do much. But what would happen is if I created an ion, yeah? What if I created an ion? So maybe we'll just make also this color coded. It's a little bit clearer. So what would happen if I have an ion? Yeah. If I have an ion, then the ion obviously has a energy that I must not draw so that it's lower than the free space energy. But essentially it's going to have a similar energy. Maybe not exactly the same, but it's going to have a similar energy. But you're going to have to add. You know, if I draw that here, you're going to have to add the sum of bloody hell, what's with my drawing today? You're going to have the sum of all ionization energies, yeah. Of all ionization energies that I need, so you know, first ionization energy, second, third, and so on and so forth. But I'm also gaining some energy, which is n times the work function. This is the work function, and this is sort of the energy that I need to set up. The thing is now that if I apply a field to the ion, then let me just draw that maybe a little bit so that we can see where that starts. So I would start here. If we apply a field to the ion, oh, that should still be a straight line, with a certain value, so the field energy would be minus n times the charge of an electron. So we've got taken n electrons out, times the electric field F, times the coordinate x. So we've got a dependency on the distance. And the energy obviously of my ion gets lower and lower and lower the more work it has done in that field. And so if we look at that, we can sum up, this part here, this function, and we can sum up this function here, and we will get to an ion in the field. And maybe that should have a different color. So maybe I'll just write, so this is ion no field, and this is atom. The atom energy doesn't change with the field because it's not charged. And if I sum both things up, so essentially this plus the field, what I will get is a function that looks some. My drawing talent isn't really all that great. So give me a redo. Yeah. Anyway, so at a very high field, we would have bent that potential of the ion with field. Sorry. And so if we look at what is the lowest energy state of the system, the lowest energy state of our particle, which can be an ion or an atom, then we'll see that the lowest energy state up to here is it being an atom, and from here on it's being an ion. So blue is the lowest energy state. And what we get here is actually that we have a barrier for field evaporation. A barrier Q dependent on the field. That is the energy barrier. And that's why I said it's so easy to adjust the field evaporation, because you essentially, with your voltage knob, you adjust the height of this barrier. You can make this barrier 0, you can make it even negative. But with your voltage knob, you adjust the height of that barrier. If the barrier is 0, obviously that's not all that helpful, because all of the atoms would want to come off at the same time, and that's not great for analysis. So essentially it means your sample blows up. But this barrier we can adjust, and we can overcome it thermally. So the good thing about a thermal overcoming of the barrier is that there's a certain probability for it to be overcome, and not every atom will want to come off at the same time. Okay, and this is essentially what this picture is showing. So we can see that the Q0, which is the entire energy that we put in, that's relatively simple. Just the sum of the sublimation energies. So it's the sublimation energy. So you need to remove an atom from the material. The sublimation energy plus the sublimation energy. Sorry, I didn't draw the sublimation energy earlier. The sublimation energy here is this part here. This is the sublimation energy. This is the sublimation energy. The sublimation energy, and this is the ionization energies. Of course, you might not just have a singly charged ion, you might have a multiply charged ion. But we'll get to the multiply charged ions in a second, so it's not that simple as here, because we still have some, the ion still has to move somewhere and can lose more electrons. And this is essentially what our total energy is. And our energy barrier, our energy barrier is this total energy, which is the sublimation energy that I need to put in, plus the ionization energies, while gaining the work function, n times the work function. And the barrier, depending on the field, is essentially this Q0, all of the energy that I need to make that ion, minus the electric field. And the cool thing here is there's actually, you see there's no X or anything in there. It's just essentially a energy, a look at the energies, which is a very, very simple way of looking at it. Some of the distances that if you apply the theory, some of the distances that are appearing don't make sense. Some of the values don't make sense. So yeah, this is just a very, very simplified view, but it will help us a lot in understanding some of the aspects of field evaporation. Yeah, and it is the barrier is this Q0, the total energy minus the energy that the ion has when it goes through that field. And this is the very simple Imagehump model. And I have to close this other window, which is currently continuously reminding me of things that I don't have time for right now. Anyway, so yeah, this is the Imagehump model. You will see that a lot in an atom probe, just because it's convenient, but it has a lot of limitations. If we look at the simple Imagehump model, then we can say, okay, what is the probability of an individual atom field evaporating at any particular time? And the probability is just a very simple Boltzmann look at things. So you have this Q of F, this energy barrier that we just looked at before, the energy that we looked at before, divided by kT, which is the average thermal energy that at a certain temperature your system or a particle has. And that's proportional to the evaporation probability. So the evaporation flux is essentially some frequency, some jump frequency, attempt frequency times that probability. And the attempt frequency will essentially be given by the temperature. And the result of that is that it's a very, very controlled process, because this I can control very, very easily. I can control the field very easily, and with that I can control the barrier very easily. And a good example here of that is this image that Mike Miller has created years and years and years ago, where he just took an atomic terrace with 9 atoms on it. I think, I'm fairly sure it was tungsten. And then he just increased the voltage on the voltage knob until it was 8, took a photo, then increased it further, it was 7, 6, 5, 4, 3, 2, 1, until the last one was gone. So no fancy algorithms or anything, just a guy with a voltage knob, controlling the behavior of individual atoms. And again, if you use the field ion microscope in our lab, that's exactly what you can do. You can stand there with the control knob and make individual atoms come off. What you don't get to control is which atom comes off, though. Again, it's a probability here, but you can control that very, very well. But we can't say, I want this atom here at the top right corner to come off, or the one at the bottom left corner to come off. The evaporation sequence is something you don't really have an influence on. Okay, so the question for us is then, okay, how much field do I actually need to evaporate something? And we can, as a representative field, we can say, okay, what's the field where this barrier becomes 0? And that's obviously relatively easy to derive just based on these considerations here. And we can see here the whole thing listed for a bunch of different elements. And for some elements, we can find this fits very well. So, for example, nickel, copper, fits very well. Niobium. But we also have some elements where it doesn't fit particularly well. Gold, for example. Gold, we should have 53, but we have 35. What else? I only took the nicer ones in. I should have taken some of the uglier ones in. Iridium, 53 is observed. 53 observed. So here we've got the observed lower than the predicted, and here we've got the predicted lower than the observed. So a comment was that the probability for evaporation for atoms sitting at the vertices are higher. Well, I think you mean at the corners and ledges. Well, the field is not constant over the entire sample. Yeah, that's not possible because you're trying to approximate a hemisphere through something discrete. Yeah? So not every atom will see the same field. Yeah? So obviously, those atoms that see the highest field relative to the evaporation field will come off first, and we'll get into that in a second. Because not every atom has the same evaporation field. Because this was is only meant for, so this consideration is only meant for pure elements. Because of course, if you have element B in solid A as a very dilute, just a very, very dilute solid solution, you can already think that, okay, maybe the work function for the electrons is not the work function of the element that we're evaporating. If we're evaporating B from A, then we can't use the work function from B. This was recognized already in the 60s by a certain Mr. Brandon. So this has been knowledge for a very long time, or assumption. It's not that precise. The thing is, the reason is, even though this theory is physically very far away from what's actually happening, it's remarkably successful. It's remarkably successful in predicting evaporation fields. And that's why you will see it a lot. And I think there's going to be a number of years before we're actually going to see much better theories based on quantum mechanics. Okay, so this was just the field dependence, but obviously we have a temperature dependence as well, because the flux here is temperature dependent, and that this near zero is also temperature dependent. So we also have a temperature dependency. So the higher the field, the more atoms come off, but also the higher the temperature, more atoms come off. And this is displayed here. You can see the relative field I need for field evaporation over temperature. I believe that was tungsten. To go back into the book, I believe that was tungsten. And you can see that at 90 Kelvin, we already have a much lower field, and at 190 Kelvin, even lower than that. And this is for, I'm fairly sure for tungsten. If this was aluminium, this would go down much more rapid. Or gallium or something, with very low evaporation field. Because, well, one thing that we can take away from this is that, what's really dominating here very often is the sublimation energy and the ionization energies. And they are particularly high for elements with high melting point, strong atomic bonding. So we see much higher evaporation fields for high melting materials than for low melting materials, just as a rule of thumb. Okay, this is a very important take-home message. Okay, and we get this change over temperature, and you can actually make a very simple assumption that close to the evaporation field, this evaporation barrier field, the change of the barrier can be approximated as linear. Just a linear approximation. You can go and use the full expression here as well, or you could, but you're not going to gain very much, just some mathematical pain. And you will see that the field to the ratio of current field to the evaporation field is essentially given by the thermal energy to Q0 in a more or less linear fashion. And this is sort of what we observe in a lot of systems. Okay, but so this was for an atom which gets ionized. So we've got conduction into the material. But what happens with an adsorbed gas atom? The difference between the adsorbed gas atom and the metal atom is that it's not essentially electrically connected, if you will, to the rest of the sample. Yeah? So how do we ionize that? Obviously it works, so it must work somehow. And the way it works is a little bit different. It's that we need to move the potential, the level of the highest occupied molecular orbital, or atomic orbital in this case, so high that there is an energy gain for this electron to tunnel into the solid. Because they're not electrically connected, it can only tunnel inside. And obviously there's a certain tunneling probability. You've probably all had some physics courses and know that the tunneling probability also goes down exponentially with the distance. And we have some tunneling probability, and we need to increase the field up to a point where this is happening. And this also means it can't happen very, very close to the atom because the field would need to be very, very high for it to happen very close to the atom. So it's kind of a trade-off between the tunneling probability that we get from having a distance here and the field that I need to move that potential up high enough so that it can go above the Fermi level of the solid. So if I have a lower field, that tunneling, that critical distance would just move further out, and the probability for that to actually happen would just go down, down, down. And since this is exponentially dependent on the distance, we need to be fairly close to here, like nanometer range close. This is why at this we have the ionization of these gas atoms in a so-called critical surface, which is a couple of nanometers above the surface, nanometer, 2 nanometers, 3 nanometers above the surface, and in between there's a forbidden zone, and in the forbidden zone, atoms can go there. It's not forbidden for them to go there, but they're not going to get ionized. There's no ionization happening in that. In that forbidden zone in between, which means that it's not necessarily the gas ions that are directly on the surface that are getting ionized, but a layer or two above that. The same thing can, by the way, happen to ions when they depart the surface. So if we look at the process, and we're seeing an ion sort of moving to the right here, then eventually that ion will also be far enough away for the electrons to be able to tunnel back into the material. This is something that's been discovered already in the 80s. This is the so-called famous Kingham Theory from Haydock and Kingham. And they have already recognized that can happen. And the thing is the same as up here. So it doesn't happen straight on top of like when the atom or the ion is very near the surface, but it needs to go a little bit further away. And this can increase the charge state of the ion. So why is that important for us? It's important for us because I said before, okay, the field that we need in order to remove the ion from the surface is strongly dependent on the temperature, or is dependent on the temperature. If we go to higher temperature, we've got a lower field. Lower field means that the point where this happens moves further out and it becomes less and less likely. Lower temperature means higher field, means this xc moves in further. Yeah? So the probability is higher. And this is the reason why at low temperatures we are observing higher charge state than at high temperatures. Yeah? Because at high temperatures this process is just less and less likely. But we can look at this in a probabilistic scale and actually calculate what it happens. And it actually goes both ways. Yeah? So I can say I'm at a certain temperature. Yeah? What is my charge state ratio? So how much charge state 1 plus versus 2 plus do I observe? Or 2 plus versus 3 plus? Or 3 plus versus 4 plus? Yeah? Or the other way around, I can say, okay, I've observed a certain charge state ratio. I know how many ions plus I have, how many ions 2 plus I have. What is the temperature I can actually calculate from that. And these are the so-called Kinghem curves. You will find them in various books, yeah, where you can see the relative abundance in this case. Yeah, probability would just mean one line, relative abundance of certain charge states. So here we've got, for niobium, we've got 1 plus as blue, 2 plus as green, 3 plus as red, and 4 plus as pink, versus the evaporation field. And if you know what temperature which evaporation field is at which evaporation rate, you can go back to that. At the first step, it's just going from charge state ratio to field, but then you can connect the field to temperature. Yeah. And you can actually find them. You can actually go into the Kingham paper and calculate them yourself, or you will find them in various books. Yeah? But this is sort of the hint why, if you use laser atom probe, for example, why do you see 1 plus and 2 plus charge states? Yeah. Whereas if you do voltage atom probe on the same material, you might just see 1 plus. Yeah? Or if you do voltage atom probe at 20 Kelvin, you only see 1 plus. If you do voltage atom probe, only see 2 plus. Sorry, there was the wrong way around. Obviously, with laser, you're going to see 1 plus, maybe 2 plus. Yeah? And with voltage, at low temperature, you might only see 2 plus or 3 plus or maybe even 4 plus. Whereas at higher temperature, you might see lower charge states. So this is a very good hint of what the charge state ratio is in your what the temperature is and what the field is on your sample. But you can also go into your sample, and if you have hints that locally you have a different field, you can check if locally the field is different. Maybe you have a precipitate with higher bonding energy, so the field is different. Maybe a higher field, or maybe a lower field. And what happens then is you can look at the charge state ratio and say, I've got locally a higher field, so maybe my surface curvature is different, or something like that. Okay. But ions don't just exclusively come off as one single ion, and this is something that's very important also when we look at detector technologies later. Because it's one of the main reasons, or one of the very important reasons, that we are getting multiple hits, which are sometimes hard to resolve for the detector. And so maybe to jump back to the question from earlier, if the probability for atoms on certain sites on the surface are much higher to evaporate, yes, because they have a larger local field. What can also happen in this case, of course, is that if you remove one atom, then suddenly the atom next to it sees a higher field and just leaves with it. Yeah, so you can get multiple hits also just simply from the fact that one atom leaves and the next atom suddenly sees more field and decides to immediately leave as well. And this is one of the of the origins of multi-hits. But we also have evaporation of molecular ions. Yeah. Especially at higher evaporation temperatures. It's not just individual atoms that get ionized, just like I suggested here, this was all individual atoms, but also small molecules can evaporate. And we are only starting to get behind of how these molecules form, like if there's surface diffusion involved, or maybe some roll-up effects where an atom rolls up one of those atomic kinks and picks up the second one, or whatever other effects can happen there. The thing about those molecules is, like, an ion cannot fall apart. a single atomic ion cannot fall apart. Yeah? It can lose more electrons, but the ion is still an ion. It's just higher charged. If you have a molecular ion, say, yeah, we've had gallium nitride before, so you can get a gallium nitride ion that can fall apart. If you remove electrons, it can fall apart. And this is actually observed. Yeah? So you can have an ion moving up to a certain point and then splitting up and maybe, but not necessarily, lose an electron. Yeah? And what would then happen is that this ion would dissociate and the two fragment ions would then impact the detector either very close in space and time or at some separation. Yeah. Very close in space and time is hard to resolve. Yeah. So if they are far in space and time, so if you for example, a gallium and a nitrogen, if they fall apart, you've got a good chance of detecting both, because one is relatively heavy, the other one is relatively light. So unless that happens somewhere where there's no field anymore, one's going to accelerate and one's going to be much slower. So this can happen somewhere inside the field, usually inside the field of the specimen, or where there's still a market field. This is actually from a paper from the group in Rouen, where they've just plotted, okay, what is the field, the electric field, versus the distance to this simulated sample here. So you've just got a sample simulated, and you can say, okay, what's my field in dependence of this coordinate z here, and you will see that up to a position of several hundred nanometers, there is still an appreciable field. So within the first couple of hundred nanometers, there's definitely still some field. But what you can also see, most of the field and voltage drop actually happens within a couple of hundred nanometers. So if something like that is happening, it's probably happening there. And what that means is that these two atoms that are then, or these ions that are separately detected, they've been traveling together for a little while. And the resulting two ions, they can have either the same charge as this one here, or a different charge. And if you remember, this might be an ion with just one charge. So if an ion with one charge breaks up in two ions, then only one ion will have a charge. That's actually been observed. There was a paper from the group in Washington State at PNNL. I think the first ones to show that you can even have neutral ions, which of course, if you for example have a reflectron which tries to move the ions back onto the detector electrostatically, these ions are just going to go plunk, and you lose them, right? Atoms there, not ions. But if you have two ions, they might travel. But they might have some energy deficit based on traveling together at a lower charge. This is something that David Saxe has found out in 2010, published. That there is if you have two ions and they travel for a little while together, and then they split up, and at a certain potential drop VD, then they have a certain energy deficit that's governed by this equation. So you get a parabola, and you can actually see those in so-called correlative ion plots. They are very often also called sexy plots, and I really urge you to call them sexy plots. It's also it's always very funny to see David Saxe cringe when he hears his own name in a presentation. But very often they're called correlated ion plots or sexy plots, where we take the observed mass to charge ratio. So essentially the time of flight calculated to a mass to charge ratio. Obviously, these ions they deviate then from the expected mass to charge ratio, or from the mass to charge ratio that they actually have. But this is sort of the mass to charge ratio that we measure, plotted, and you see that the parabolas that we get, they end in the individual ions that are making up the ions. So either either they break up very close to here, then we just get the mass to charge ratios of the two ions that are happening that make that up. Or if they don't break up at all, it will end up in the combined ion. And we have a parabola, sorry, not a parabola, a hyperbola connecting the two ends. Of course, if you don't look into that correlative ion analysis, and if you just look at the mass to charge, this is mass to charge ratio of one ion, of ion 1, and mass to charge ratio of ion 2. Yeah. And in this original plot, it's actually not sorted by which one arrived first and which one arrived later. Yeah? Otherwise, it would only be one diagonal here. Yeah? It would sort of end at A equals B, sort of at the equality line. Yeah? Either top or bottom, depending on which one you want to see first and which one you want to see later. But what you can see is that all of the ions that are impacting on a detector on this parabola, they're usually not really allocated correctly to the the species that they actually are. So using this technique, you can actually recover. And identify ions that you wouldn't be able to identify otherwise. The limitation hereby is we do not have 100% detector efficiency. Yeah? So imagine your ion splits up into two ions. Yeah? And say the detector efficiency is 0.5. Yeah? So if you have, if you have a LEAP 3000 or 4000 SI or a 5000 XR, that's about the detector efficiency that you have. Then the probability to, if the probability to detect those ions is, there's a probability of, there's a probability of 0.5 for each atom to be detected. Yeah? So there's a probability of 0.5 squared, or 0.25 for you to actually catch both of them. Yeah? So there's only a relatively small probability for you to catch both of them. Yeah, the probability to catch the first one is also 0.25. The probability to catch the second one is 0.25. So the probability is 0.5 for you to catch one of them. Yeah, either the first one or the second one, and the probability is also 0.25 that you catch none of them. Yeah? And obviously, this gets more and more complex the more ions, the more fragments you will get. And obviously, this analysis also gets visually a bit more complicated once we're talking about more than two fragments. In two fragments, it's nice two-dimensional. See everything there. Once you talk about three fragments, obviously you need a three-dimensional plot. And then also the individual hits that you have here will also spread up in 3 dimensions. So it gets really hard to see if you see this parabola. Hyperbola. But in principle, this can also be observed for 3 fragment processes. But this has become a very important tool, especially in atom probe samples where correlated field evaporation happens a lot to recover some of the ions. Not quite sure if you recover everything, but you can recover some of the ions. And this is especially prevalent in compound semiconductors, in oxides, in anything with covalent bonding. So a lot of the modern laser atom probe that we do, we're confronted with that a lot. And it goes really far beyond the introduction today. They go to dive into that a lot deeper. I hope there's going to be an IFAS lecture just on this, uploaded pretty at some point. Wana Koyao Medin from RWTH Aachen has made a very nice presentation about that. Okay, so this was all under the assumption that we have a certain field that terminates at the surface. Yeah, right. So the sketch here was, okay, we've got a field and the field terminates at the surface and that's all the influence we have. but that really only works if I have a charge density or charge mobility that's high enough for that to happen. And for semiconductors and insulators, that's not actually the case. Yeah? For semiconductors and insulators, you can't just move enough electrons to the surface to have no field inside. Yeah? Instead, you will actually have a field inside. Yeah? So this is dependent on the debye distance, so we're not going to go into the details of bending, but you might know that from semiconductor devices. The reason why a transistor works or why a diode works is because we've got permanent electric fields in those devices. And if you put a field onto a semiconducting or non-conducting samples, we will also get those internal fields. And we'll get those internal fields because you can't move enough charge around. This means that, for example, if you have a non-conductive particle in a conductive matrix, you're going to have field lensing inside of this particle. Some very nice papers from the group in Stuttgart about that. And what you can also have is that if you have high mobility species in your sample, then this species can move around. And this is what I meant, this is one of the things that I meant when I was talking about we assume that atoms don't just come and don't just evaporate from the depth of your sample, but in nice order. Yeah? But in some cases, if you have an electric internal field, you can actually have field-induced migration. And there's also a very nice paper from the group in Stuttgart where they've shown that to be the case, for example, for lithium in glass. Yeah? If you analyze glass in the atom probe and you have lithium, then the field inside the glass is high enough for the lithium to be pulled around in the sample. Yeah? So you can completely explain the concentration profile you get in your atom probe measurement just by the internal electric field and the diffusion of the lithium in the internal electric field. In metals, the field terminates at the surface. Yeah? Semiconductors and insulators, it does not. Okay, but the field doesn't, of course, the field obviously exerts some force on the atoms. And the question for us is, does it make the atoms move inside? But it's also the question of, does it break our sample? And there's a very nice derivation of that in the book from Miller and Forbes, where they show as an approximation the pressure difference between the inside and the outside of an electrically charged liquid. This is just an approximation for us. Is proportional to the field squared. The radius here, just the principal radius of curvature. In our case, it's R1 and R2 should be the same. R1 and R2 should be the same. So we would have 2 over R1 in this case. And the surface tension. But the important thing for us is it's proportional to the electric field squared. The pressure is proportional to the electric field squared. And you can actually from that also calculate what the stress in the sample is. And you see the stress is closest to the tip, and then it goes down to some extent. And unfortunately, I didn't have access to the old paper by Charles Moy from Sydney, who has done a very nice simulation on that. And you would also see that the highest stress in your sample is not at the surface, but a couple of nanometers underneath the surface. It's similar to a Hertzian pressure, if you know some mechanics basics. It's very similar to that. So that the highest stress is not necessarily on the surface, but a little bit underneath, which can lead to little chunks of sample fracturing off. If you've got a very soft material and that has a relatively high evaporation field, that stress can lead to entire chunks of sample fracturing off. The good example is if you've ever tried to measure gold in the atom probe, that's exactly what happens. You get chunks of gold coming off. Okay, so up to now, the assumption was that the evaporation field is sort of a constant across our sample. And this is only the case, really, well, it's never the case because, if atoms are sort of bonded, if atoms sit at ledges of the atomic steps, then they have a different bonding energy than a single atom just sitting on top of a free surface. Yeah? So that's already not true. But what's coming on top of that is that actually, well, what if you have different materials in there? Then it's pretty obvious that they have different evaporation fields. Yeah? And all interesting materials actually look like that in the atom probe. The reason being is, well, we want to analyze something in something, yeah? And so this something is going to have a different local bonding structure, and with that a different local evaporation field. Yeah, and what will happen is that depending on whether the evaporation field is higher or lower, it will either stick out, yeah? And with the sticking out, it will have outwards pointing electric field lines, yeah? Or, you know, if it's sort of caving in, it will have inwards pointing electric field lines, or it will be focusing. Yeah? And this is what we call local magnification. And this is probably the most important effect for us that's limiting the resolution in atom probe tomography. Yeah? Just a mere fact that we will have things sticking out or have things sort of being indented. And thus the field lines either lead into focusing, and with that a smaller size of the image, or it poking out, and with that a larger image. That's why it's called local magnification, because this comes all from the days of precipitation, and precipitates tend to have a higher, more stronger bonding. That's why they precipitate in the end, and with that they are getting magnified. This is typically what we see here in our atom probe data. Here we have one where we see locally a higher hit density. Which means we have a demagnification. So this is a histogram of detector hits of a certain slice of atomic hits. And you can see here, okay, we've got a higher hit density here. And if we look at resolvable features, size from APT versus real size, you can see that typically when we go to very small objects, then our deviations are in the range sort of from 0.5 to about a nanometer and a half. And this is ultimately pretty much what's limiting our resolution in XY. Additionally to that, we can also get chromatic aberration. Chromatic aberration here is maybe also a bit of a misleading term because it's not actually some wavelength dependent thing. But what that means is that if you are evaporating something that consists of more than one atom, type of atom, then atom type A, in this sketch here, might come off easier than atom type B. What that means is that atom type B sees a little bit of a different electric field than atom type A. You know, just by a smidgen, just by a little bit, but it is selective to the actual atom. And if we additionally have that that feature where that we look at not smack bang in the middle on the top of the specimen, but somewhere on the side, where the field is not this pointing sort of a little bit sideways, then we get a shift into where we see this effect. This is sketched out here. So this is silver and aluminium. And ideally, you would see the silver and so you would see a drop of the aluminium exactly where the silver is. It's a very nice precipitation system because you get actual silver precipitates. I think it's Ag3Al. I hope there are no aluminium people here that will correct me immediately. But you have local magnification on top of that. So they are precipitated a bit larger. But because of this effect, of this chromatic aberration effect, you also see a slight shift between the position of silver and aluminium in this case. And obviously, if you then create a concentration profile from that, you would falsely assume that there is some kind of enrichment, local enrichment of species A or species B somewhere at the interface, whereas all that is happening is actually this chromatic aberration here. So this is especially important to keep in mind when you're looking at precipitates. Good. So this was all in XY, but do we also have some limitations in Z? And the answer is yes, we do. And the reason for this is whether we have sticky atoms. Yeah? So especially atoms that are not locally chemically bound, they can diffuse a bit on the surface, and especially if they're hard to ionize, like boron, for example, or carbon. Yeah? So they're atoms that are relatively hard to ionize. They might stick around for a little while, and this is what we call preferential retention. Yeah? This is actually something I had to painfully discover, because I wanted to actually look at where atoms are in which atomic plane relatively to a grain boundary individual atoms are, and all I found out was, well, we can't tell with atom probe. It's really fundamentally impossible, because the atoms can stick around for a little while on the tip. Yeah? Can stick around for a little while on the tip, and here this is actually plotted for a couple of different elements. This is boron in, I think, a nickel-based alloy. This is carbon in the same alloy. And this is, for example, copper in an aluminium alloy. But what we also observe is that there's a certain constant probability, yeah, for it to evaporate at any different point in time. If you have a constant probability, then the amount of flux that you get is proportional to the amount of stuff that you had at a given point, which means you get an exponential decay. Yeah? This is the so-called retention function, and here there's the actual concentration profile that's observed. Yeah, and this tail here, that's always coming from this retention. You can see that, for example, the boron has a different retention function, the carbon or the copper on the copper on the aluminium. But this retention function is obviously convoluted with the real distribution of the element. So in this case, the analysis direction was always downwards. Yeah, so it's getting retained there. The thing about that is it's not actually easy to determine what to just relate the retention function, essentially the proportionality factor of this exponential decay, with the nominal evaporation field of the solute relative to the matrix. There's sort of a trend that the harder the solid is to evaporate, the longer it gets retained. But for example, if you look at carbon in nickel, it doesn't stick, but carbon in iron, for example, sticks a lot more. This is obviously partially due to the fact that our theories for evaporation fields are highly flawed, but it might also have other reasons that we currently don't know. That it is sort of a constant probability. We can just show that if we take this concentration profile that we observe, and we just deconvolve the retention function out of it, then we get something that looks a lot like a concentration profile, like we would expect it for example for the copper at the aluminium grain boundary, like this thing here. What we also learn from that is that concentrations at interfaces in atom probe tomography are not a good measurement for anything. Yeah, they're not a particularly good measurement for anything, because the way that this retention happens, it will always be different depending on whether the interface is this way relative to a measurement direction or this way to a measurement direction. Yeah. So if you work with interfaces, do not quote concentrations at the interfaces. Yeah, or maybe very cautiously. Yeah, but they're not a good measurement of what's actually happening. But if we just count how many atoms are there that wouldn't be there if the interface wasn't there, that's a much more robust value. Yeah, and that's why we are going to be looking at interfacial access values and interfacial access mapping tomorrow on Friday, just simply because concentrations at interfaces are not a particularly representative value. Yeah. So you might be, if you interpret a lot of that, you might just be chasing ghosts. Yeah. Okay, so there was a lot of information about what can go wrong. Yeah. But this is really something you just have to deal with when you're doing APT. Yeah. Just keep those in mind. Read up on those effects. I think there's a bunch of papers on this effect now. On the chromatic aberration, there hasn't been that much literature since the original paper by Emmanuel Marquis and François Warpillot, which is now 15 years already old almost. But this is something to keep in mind, and I think local magnification is something that everyone has in mind, and it's something that we can work on with the reconstruction, because this is mostly an artifact that preserves the neighborhood relationships between atoms. They can get broken if it's an extreme case, but for the most part, neighborhood relationships are preserved. Here, neighborhood relationships are broken, but they're not broken by a massive amount, maybe a nanometer or two. So as long as you don't start looking at, which atomic plane stuff sits in, you're kind of going to be all right. This effect is breaking neighborhood relationships, because one of the boron atoms that came off here is probably 2 or 3 nanometers away from its original neighbor in the reconstruction, or when the field evaporates, it's already a couple of nanometers away from its original neighbor here. Obviously, the probability for it to stick around for that long is relatively low, but it's not zero. Again, this demands some mobility of the atoms. So if you're looking at atoms that are locally very strongly bound, then this effect plays less of a role. Okay, so the last question we're going to look into in this part of the session is, how do we get a reference time? So we already looked into our basic field evaporation theory, Imagehump model, and we've seen, okay, we can have different evaporation fields depending on temperature, and depending on the field or on the voltage, more accurate it would be the field, which can be different locally. We get different evaporation rates. So this is a sort of band. So you could essentially go and let me just draw that. Maybe that it becomes a little bit more clear. And we are going to need a new sheet. Yeah. So if we go field F versus temperature T, if we look at our, let's do it in color. Let's say we have, and always excuse my choice of color. So for our atom A, we might get, at this field, we might get 1 ion per pulse. At this field, we might get 0.1 ions per pulse. And at another even lower field, we might get 0.01 ions per pulse. This is what's meant with evaporation rate, or ionosublimation rate. And then we might have let's take an existing one. We might have an atom B, and where we might have the same thing happening here. And one thing that is, if you go back to the original theory, you can derive for yourself, is that the lower the evaporation field is, the higher the slope here is, okay? The higher the slope here is. So the difference in evaporation field gets worse the higher the temperature is. It's always something that's important to keep in mind. And so we might have our sample at a particular voltage, and in a particular state when we start measuring, we don't actually want anything to evaporate between the pulses. So this is our F from voltage from our DC voltage. So we have a DC voltage applied. The DC voltage applied, and this is where we're standing with our DC voltage. And it's important that our DC voltage is below any appreciable evaporation rate of any of the species in our sample, because if any of the species evaporate at this field, we have no time correlation. We didn't know when it left. We'll just impact at a random time on the detector, and we're not going to be able to say whether this was a cosmic X-ray, whether this was radioactive decay in the detector, or whatever else. We're not going to be able to tell it apart because it's not going to have any time correlation. So we need to make sure that our DC field, is always low enough so that none of the evaporation is at any rate that is relevant. And if we do voltage pulsing, what we do is that for a short amount of time, we apply our pulse voltage. For a short amount of time, we apply our pulse voltage, or in this sketch, our field from the pulse voltage. Obviously, we want to do that, as much of a rectangular function as possible, but we're going to see why it's hard to make that a very rectangular function. And how long do we want a pulse to be? Do we want that pulse to be a nanosecond, 10 nanoseconds, 100 nanoseconds, microsecond? And the other thing we can do, or in principle anything in between, is we can increase the temperature. We can increase at a standing field. We can go to a T peak, to a peak temperature, or any temperature in between, and make the field evaporation that way. Which means that we have a delta T here, a delta T from our laser. This is going to be laser field evaporation, that needs to be high enough that the voltage pulse needs to be high enough that also we don't have the effect that we just evaporate one type of atom and the other one sticks. And the same thing about the laser power. We need to have enough laser power to evaporate everything. And to raise the temperature high enough. And obviously, that this is pulsed laser, APT, and this is voltage, APT. But, all we need is we need a pulse that gets us into the, maybe with a little bit of colors that it doesn't get too overloaded. All we need is, to get in this pulse region. This pulse region, which could in theory be any combination of temperature and voltage. It could be any combination of temperature and voltage. So far we've done exclusively pulsed laser, exclusively pulsed voltage, but Chemica in the latest iteration in the LeapTech 6000 has given the ability to combine both. Maybe it helps, I don't know. There were some experiments where the group in Rouen has done that a couple of years ago, and I don't remember it to be anything that they pursued later. So I don't know. Maybe we'll learn something. I don't know. Having the option is cool. Having the option is cool. We can also do it on our instrument, but I so far had no reason to do it. But anyway, we're gonna have the ability to do that, but so far there wasn't any reason, anything that was really motivating to do that. But essentially, you could say that You know, this is the VDC region, this is the pulse region, and this is the no-go region. Yeah, what we don't want to do is we won't want to be in this no-go region. Yeah, we want to go from the VDC region. We want to go from the VDC region into the pulse region, and do not go into the no-go region. We need to always come up with measurement parameters. I mean, for a lot of systems, people have spent, have solved those issues decades ago, and you can say, okay, we know pretty much exactly, what kind of pulse fraction that we have that gets us into the pulse region and not the no-go region. Yeah. But for laser, this is always a bit more of a debate. The funny thing about that is you will probably see a lot of atom probe papers saying, okay, we have a pulse fraction of 20%. Yeah? And you might ask yourself, why? The joke about this is that I think in the late 70s, early 80s, there was a round-robin experiment between a lot of labs where they've determined the minimum pulse fraction to get the correct chemical composition on, I believe it was steels. Yeah? Probably some of the older people might have some comments on that. And they have found that I think 17% or something like that was enough to always get the correct answer or the expected answer. The problem with that round robin is that it's never been published. So the whole thing of use 20% has been around in the atom probe community for 40 plus years, even though the work behind it has never been published. Yeah. So maybe as a hint why it is that way. Yeah. But there's nothing wrong with you doing your own experiments, varying the pulse amplitude, yeah, or varying the temperature, and trying to find out where the pulse region is, where the no-go region is, and essentially where the no-go region ends and where the pulse region starts. Yeah. The boundary between the no-go region and the VDC region is relatively simply 0 pulse. Okay, good. And this is this whole diagram maybe a little bit more complicatedly built. Okay, so let's jump into voltage atom probe, and there it's a little bit it's relatively simple. So in voltage atom probe, what we have is we have a high voltage pulse, yeah, that we couple into a specimen via some electrically impedance matched line. Yeah. So in modern atom probes, it's usually just a 50 ohm line. In old atom probes, it used to be 75 ohm. You don't have to worry about why one or the other. Yeah. But anyway, it just needs to be kind of like a data line where you have high frequency communication. Yeah. You need to have a electrically very well matched system, so you don't get any pulse reflections in the system. But that's, you can buy that stuff. You don't have to worry about that all too much. You just have to buy it so that it can withstand a kilovolt pulse. Because usually data communication where these cables are used is usually not kilovolts, but rather single digit volts. Yeah. But because our pulses are so short, mostly they're actually fine with that transmission. Anyway, so you're going to have some kind of pulse, and here the pulse is modeled as a product between two exponential functions of different decay. Yeah? So it's this dashed line. And if you take our theory from before, you will see that the evaporation is actually limited to the very top of this pulse. Yeah? Ideally. Yeah. But of course, it could happen a little bit earlier, a little bit later, yeah. And depending on how early it happens, the amount of field that the ion sees before it leaves the area around the specimen is different, yeah. So you might have an energy difference or you will have an energy difference between ions that come off very early in the pulse and ions that come off very late in the pulse. Obviously, this is worse the longer the pulse is, and this is why we want to have relatively short pulses. So you want to have pulses that are long enough for an ion to actually ionize. If you got extremely short pulses, the ion is not going to have time to ionize and leave the surface. You're just going to polarize it, and then the field's gone again. So it needs to be long enough for that, but other than that, you want it to be as short as possible. Also, we would like it to be just, ideally the pulse would just be a rectangle pulse, so that we have a constant probability on the pulse, or a delta function essentially. But real pulses don't look like that. They look a little bit like the one here. So this is actually our 200 kilohertz, 3.5 kilovolt pulsar that we're using on our Oxcart atom probe. And you can see the pulse is about, so this is, I hope you can see that well, but one diff here is 1 nanosecond. So you can see the pulse is full width half maximum, about a nanosecond and a half. And it has a rise time of about 550 picoseconds. And this is if you think about it, it's 550 picoseconds for 3,500 volts. Yeah. So this is an extremely steep rise in voltage. But if you have a well impedance matched system, you can actually get that pulse without much loss in rise time. At least I can't measure any loss in rise time with my equipment that I have here. If you have a very high-end oscilloscope, maybe you can tell the difference. But with the oscilloscope that I have, which is a 1 gigahertz oscilloscope, I can't measure a rise time difference from the pulse going into the system and coming out of the system. This is about what we get. So the shorter your pulse is, the better the rise time is, the better your resolution, your time resolution, or the smaller your energy differences are going to be, and the better your mass spectrum is going to be. But you're still going to have some energy deficits, and that's why we have the reflectrons, and we're going into reflectrons in the next session. And this is why this whole bit was relatively short. So the question is now, what happens when we have pulsed laser atom probe? When we have pulsed laser atom probe, it's a little bit different. Obviously, so the reason why we want to have pulsed laser atom probe in the first place is that, I told you here that the voltage rise, the field rise, is extremely rapid on the sample. And if your sample doesn't have enough conductivity, we're gonna have some effects because it's kind of like having a little capacitor. It's kind of like having a little capacitor, and it will get resonances. And these resonances, they will just break your sample. And so you might get a couple of atoms coming out, but it will blow up pretty soon. Yeah. So if you put if you put silicon dioxide into your voltage atom probe, you're gonna get a couple of atoms, and then it will just blow up. So we need laser atom probe because here in this case, what we do is we don't change the field. Yeah. The field, we put the field in via DC voltage, so very slowly. And through this very slow process, just charge hopping on the surface and other surface conductivity effects are going to be more than good enough to get the potential to the tip of the surface. And then we'll just increase the temperature and get the time correlation from this increase in temperature. Again, if you don't care about time correlation for whatever reason, you don't need a laser pulse. You can do whatever material you want, no laser pulse. Laser pulse is only for the time correlation. And the breakthrough there came by using femtosecond laser pulse, so very short laser pulses. In the early days of laser atom probe, in the 80s, it was nanosecond lasers, infrared lasers. Now what we have are UV lasers that are picosecond or femtosecond lasers. Maybe even attosecond lasers, who knows? Anyway, in commercial atom probes, we have, I think, picosecond lasers, or maybe already femtosecond lasers. I think the pulses on the 4000 series were sort of 10 picoseconds. Is anyone from Kamika here that can confirm that? Not that I'm saying anything stupid. Okay, just correct me at some point if you if you know what the pulse duration is. I think I remember it to be something like 10 picoseconds. Anyway, there was a relatively wide range of times around that where it wasn't found to be a huge difference if it's 100 femtoseconds or if it's a couple of picoseconds. Doesn't really matter. So all we do is heat up the sample, and that was actually something that came out of a PhD thesis. So if you think your PhD thesis is not going to be important, our friend Baptiste Gold, he was actually doing this with his colleagues in France as his PhD thesis. And funnily enough, all of the data from his thesis was acquired in 1 week where they had borrowed the laser. Yeah, so it wasn't even their own laser. Anyway, so what you can do is you shoot your laser onto the sample, and through the short increase in temperature, which you want to be as short as possible, you get the atoms to field evaporate. And with this laser, you can see you get your 2D distribution and you get your atomic resolution just as before. Maybe. Yeah. Here with the tungsten, it works, but it doesn't work with any sample. The good thing in this case, though, is if you want to increase your temporal resolution, the time that it takes your sample to cool is constant. It doesn't matter if you, unless you pulse very, very short, like if you would pulse every 5 nanoseconds or so, which is completely pointless because then, we'd have 5 pulses before the atom even hits a detector. Just as a hint, typical flight times in atom probe are between 50 picoseconds and 1 or 2 microseconds. 50 nanoseconds and 1 or 2 microseconds, depending on the flight path length and what element it is and what voltage and so on. And so you need to give your atom enough time to fly before you send in the next pulse, because otherwise you don't know from which pulse the atom came from. But if maybe you have a system where you could still figure that out, then you can work with very high pulses. I don't know. Would be something that's definitely possible. Anyway, and this is sort of the limitation. What that means is that the insecurity in allocation of the flight time to the master charge is constant with respect to the pulse. So the longer your flight time is, the better the ratio of time of flight to insecurity in time of flight becomes. So if you make an extremely long flight path, you're going to be extremely precise in your time of flight measurements, in your allocation of chemical identity. And the most extreme case of that was actually by Tianzong in Taiwan in the 80s and 90s, who had an atom probe, mind you, not a 2-dimensional, not a 3D atom probe, but a 1-dimensional atom probe with an 8-meter flight path. Where the ions would fly at 8 meters before they hit the detector, and that would allow for extremely precise allocation of master charge ratios. Of course, these days we want to have a 2D resolution as well. So unless you can make a detector that's like a meter in diameter, you will have to place it somewhat closer to the specimen. Here also the reflectron helps. The reflectron doesn't actually per se do anything in laser atom probe, but because a lot of the reflectrons, especially the ones from Kamika, are focusing, not defocusing, you can have a smaller detector sitting somewhere, and the flight time gets longer by the atoms flying into this bucket that's the reflectron and then coming out again, and this way flying long. And this is why you also get a better mass resolution in laser from a reflectron compared to a straight flight path instrument. It's just because the flight time is longer. If you would take a straight flight path instrument and just put the detector very far away, you would have the same effect. And that's what we would see, for example, with the new generation of Kamika atom probes with the focusing optics and everything. We're probably going to see some pretty great mass resolution as well. But we could also buy a really big detector and put it very far away. I mean, there is now a company that makes microchannel plates with 20 centimeter size. We could make an atom probe from that. So what is limiting this insecurity in time? It's essentially thermal conductivity. Yeah. So you heat your specimen, yeah, and this is just a simulation of the heat conductivity. And you can see the temperature, the temperature versus time on that tungsten specimen that was measured by our colleagues in France. Yeah, and so essentially the evaporation probability, that's temperature dependent, and we looked into earlier, essentially follows the temperature curve then. Yeah, and this is where your insecurity in timing essentially comes from. Yeah? At which point in time does the atom come off, depending on its temperature? The thermal movement, the thermal energy you give to the ion plays no role, no appreciable role. Yeah? What is important is that all of the ions and have essentially within the accuracy of the power supply is going to have some ripple to it, but within this accuracy, they're all going to have the same energy. Except for the whole ion dissociation thing, yeah. So this also plays a role with the energy, but let's assume single atom ions, then they're all going to have the same energy. This also means, of course, that the flux of atoms is strongly dependent on the peak temperature that we heated up. So here we see, okay, if we increase the energy flux, if we increase the flux of ions, so that of photons into a specimen, we get a more or less linear dependency with the peak temperature as well. And yeah, this is a strong hint for the thermal nature of the evaporation. So the question is now, what can we do then to improve the measurement quality here? And here it's mostly the effect of the laser wavelength. Yeah. So again, we have the thermal pulse, and we want the thermal pulse to be as short as possible, just like we want the voltage pulse to be as short as possible. And if you actually shoot a laser onto a specimen, which is a sub-wavelength, at least for now, a sub-wavelength antenna essentially, then the maxima of the absorption are dependent on the wavelength. This is work from Jonathan Jonathan from the group in Rouen as well. It's already also 12 years old, where he has shown that if you make that what is really relevant is where the first absorption maximum is. Where the first absorption maximum is, and the shorter your wavelength, the closer this absorption maximum is to the apex. Yeah. So imagine here, this is infrared light. Yeah. So with the infrared light, you can see this is your tip, and you're heating behind the tip. Yeah. And the heat has to travel from here to here in order to cause the field evaporation. Yeah. So first of all, you need a lot more heat. Yeah. And also you need the heat to travel from here to here, and then all the way back for it to cool, because of course the cooling is sitting here. So you're not cooling it from the outside, you're just cooling it where you're holding the specimen. And so the heat needs to move out here. And so the shorter the wavelength is, the closer the maximum of this heating moves to the tip apex. And this is why we like shorter and shorter wavelengths. So this is why we've moved from infrared to green, to UV, to near UV, to deep UV. This is, by the way, not the end of all wisdom. This is just a ballpark, but we have anecdotal evidence from various groups that sometimes infrared worked better than UV, for example. So it's not said that this is always the best way to do it, but this is, in tendency, it's better to have a shorter wavelength. That's why, of course, for example, the instrument manufacturers have pushed for shorter and shorter wavelengths. But currently, we're on all regularly operating instruments, we are working with thermal pulsing. On the horizon, with extreme ultraviolet light, we have direct ionization processes. Where we directly ionize, and we have athermal processes. This would be extremely important for us, because then we don't have all of those heating issues here, because the peak temperature also means that you can get diffusion on the surface. But for now, this is what we have. And here we see the difference between different instrument generations from Kamika, for example, where you have a LEAP 3000 where you had, first of all, a larger spot. Yeah? So you put in more energy in total. Yeah? Of course, if you shrink your spot, you also put in less energy in total. And a longer wavelength on a, I think, 10 picosecond pulse. And you can see these thermal tails that we get are appreciably larger than on, for example, a LEAP 4000 or LEAP 5000 instrument, which has a much smaller spot, about a 3 micron spot, because you've got in situ optics, and a shorter wavelength as well. And this is the marching direction, of course, and this is silicon dioxide, silicon and silicon dioxide. And of course, what we want is ideally to have completely athermal processes, because then obviously a lot of the artifacts that we have would vanish, because remember, the evaporation field differences get larger the higher the difference is. This means all of our artifacts, local magnification and so on and so forth, get worse. So everything gets worse at higher temperature. So we want to be at the lowest temperature we can, but for a lot of the samples we just have to use the laser, and we have to use certain laser energies in order to evaporate all of the species that we have. But if we could get rid of that, that would be the biggest thing since sliced bread for atom probe tomography. Okay, so this was the basics of field evaporation physics. I hope you understood the main things that sort of bother us in APT when we do our measurements, and I hope you understand a little bit more about your data then. But for all of those effects, there's a lot of literature to read up on if need be. But I hope this gave you a bit of a good introduction. And with that, we're actually ready for lunch. So my question to you: do you have any questions that you have? Any follow-up questions? Probably a ton of them.
I would have a question.
Yeah.
First of all, thank you very much for the nice explanations. Just a really basic question. During one laser pulse, is always the whole specimen irradiated or only the tip? And if so, how does the refocus or the repositioning of the laser works?
So that depends on what instrument you're working on. So if you're working on a commercial Chemica atom probe, the laser is focused down to as small a spot as was engineering-wise possible for this setup. So we're talking about 2-3 micron spot. Obviously, a spot is not a delta. It's not a perfect square function, but you have a drop off. But that's not necessarily the case in other instruments. For example, the group in Rouen uses lasers with a millimeter diameter, where you irradiate a much larger spot of the specimen. And the early experiments that you saw were completely non-focused lasers. It also works if the laser is not focused. But depending on what laser you have, so if you go to short wavelengths, you need up conversion. You need up conversion, and you lose a lot of laser intensity during that up conversion. So partially you need to focus to a certain extent in order to have enough laser flux left. This is one aspect, and the smaller the laser is, the smaller the total heat input is that you need to reach the temperatures that you actually need for field evaporation. Obviously, if you would move to a laser with a short enough wavelength that you have direct ionization processes, and you have enough flux in that laser, you wouldn't need to focus anything. But for now, we need to focus for that reason, or we usually focus for that reason, but it's not a necessity. So the focus position is actually controlled in a variety of ways. So in the Chemica atom probes, the focus position is controlled by just moving the focal spot around and looking at where you get the highest field evaporation, the highest flux of atoms. Because then it's sort of ideally positioned, if you will. That is one way of doing it. Then the colleagues in Stuttgart essentially have made the laser a confocal microscope. So they can position the laser using essentially confocal microscopy. Our colleagues here in physics that do very similar experiments, they essentially have complete optics, complete imaging optics to do that. So it always depends on what your setup is. I think one of the best setups I found for that is one that our colleagues here in physics in Erlangen have, which is the direct optics, because you essentially see an image of what you're doing and you align your laser, and it doesn't matter how misaligned your specimen was, it doesn't take very long to align it. But I think the version that Kamika does it is also very practical. Obviously, many of you are using it out there, and it's much easier to integrate in a system.
Okay, thank you so much.
Yeah, we've got more questions.
Yes, please. It was a very nice talk. Thank you very much for your explanation. It was very clear. I was just wondering, on slide 20, you were talking about you measuring the shape of the pulses using an oscilloscope.
Do you mean this one?
Yes. Can I ask you, how did you connect the oscilloscope? Like, did you need to open the chamber or whatever?
No, well, it depends on where you're terminating your pulse. So in the Kamika atom probes, the pulse is terminated internally. So there is a big 50 ohm resistor in the chamber where the pulse is terminated. So the pulse essentially goes into the chamber and never goes out again. We're doing it a little bit differently, and most other people as well, is we have the pulse go into the chamber and then go out of the chamber. And then you can just put an oscilloscope at the end of the pulse line. That's actually, well, you need to attenuate the pulse, because if you put a 3 kilovolt pulse into your oscilloscope, it will just go up in smoke, and it's going to be a very expensive oscilloscope for that purpose. But you put in a series of attenuators, high frequency attenuators there, and then you put your oscilloscope there. If you want to do that on a Kamika atom probe, you can do it in a variety of ways. You can either connect directly to the pulsar with some attenuators. We've done that during some pulsar repair back in Sydney. Or the other way you could do it is to put a pulse picker in there. So you can put a pulse picker, for example. You have the transmission line, which is usually a 50 ohm SMA cable with SMA plugs. And you can just put a pulse picker in there. For example, a 1-2000 pulse picker where you have 50 ohms on the straight line, and then you might have 50 kilo ohms on the pickoff line. So you can get it out like that. In this case, the image that you see here is actually done with a proper high voltage attenuator, with a BART attenuator, with a very high bandwidth, by our colleagues in Russia that built the pulsar. The downside of those BART attenuators is they can only do very low pulse repetition rates, and they're very expensive. So I've never bothered buying one because we can just put it in the end of the pulse line.
Okay. Oh, thank you.
Yeah, next question, Mr. Ding. You were next in line, I think.
Yeah, thank you very much, Dr. Pfeffer, for the nice detailed explanation. So I have a question regarding the preferential retention. So you talked about it because of there is like preferential retention at the green boundaries. Yep. So my question is, does that mean that using atom probe to measure the green boundary segregation is not a good method?
No, that's not the case. Not the case at all. So first of all, it's the only method. Yeah. I mean, you can do some electron microscopy, but that's going to be very hard to quantify.
Yes.
So what is just not a particularly good idea is to use the grain boundary concentration as the ultimate measurement. If you count how many atoms do I have that it wouldn't be there if the grain boundary wasn't there, it's still a very valid measurement, because if you look at the graphs down there, you can see the development of concentration with depth. If you integrate over that, it's still a fairly reliable measurement. But just looking at how tall the peak is, that obviously depends on what the retention coefficient is. That depends very much on that. But the overall amount of segregant, that's still the same. We can be relatively confident we capture all of that. It's not completely out of the question that some atoms just don't leave. I don't know that. We assume that the ionization rate is 100%, that we ionize everything. but there is no guarantee for that. It's an assumption that we make. It's a relatively well-established assumption, but it's still an assumption.
Okay, thank you very much.
Mr. Forbes, I'm pretty sure you found plenty of flaws with my explanation.
No, I think it's very good, Peter, but I would want to clarify one thing. That's about Imagehump. Can you go back to the relevant slide?
And I would very much encourage you to record a lecture on field evaporation theory. That would actually be much more complicated than mine.
Okay, that's the one. You've got to distinguish between the Imagehump model, the Imagehump mechanism, and the Imagehump formula. Now, the mechanism you're showing is what is normally called the charge hopping mechanism.
Yep.
But there is a second mechanism which has been discredited, which is the Imagehump mechanism, where it goes over a hump. Now, the formula you've given is exactly true for the Imagehump mechanism, but it's not exactly true for real ones. But you shouldn't use that. But there is a formula for evaporation field, which is on the next slide, if you can go to that. No, somewhere else there was.
Yeah.
That's the one. That is sometimes called the Imagehump formula, but you cannot actually validly derive it physically from the Imagehump mechanism. You have to derive that from thermodynamics. It is derived from 3 terms out of about 7 terms. Yeah. So it's an approximation, 50% factor of 2, but you know, it's okay. We will never get a correct formula until we have better quantum mechanics. And I agree with you, that's a few years off yet. So all I would say to people is be very careful with the terminology Imagehump. I personally prefer to call that formula the basic thermodynamic formula.
Yep. What Professor Forbes was alluding to is the difficulties that we have with quantum mechanical theory is here that we have a high field. So usually if you see quantum mechanical simulations, you have to terminate it at some point because essentially the computational expense goes with the 7th order of the physical size of the system. So, you know, simulating 100 atoms is quite fine. 200 atoms is off the charts. And so usually what we need is we need to have some kind of symmetry that we use in order to be able to come up with the simulation. And that symmetry is in principle broken as soon as you have a field, because the field always goes into one direction. So you can't have something like periodic boundary conditions very easily. There are tricks with mirror charges that you can do, and actually this was pioneered by Professor Neugebauer, who was at MPIE already 20-30 years ago, with a completely different purpose. He was doing electrochemistry, but that's been fortunately resurrected in the last couple of years, and we're starting to see some good results coming out from that. But the problem is still, you know, 100 atoms or 120 atoms is not a lot, and 200 atoms is out of reach. And this is really the problem that we're facing here.
There is actually a second problem in that when you have a field evaporating atom, it's missing 1/3 of an electron. So where is the electron? The electron is around on the walls of the vacuum chamber, or alternatively on the local electrode. And theoretical physics finds it very difficult to deal with situations where part of an electron's centimeters away. Yeah. And that also is a second problem that's not solved in my view.
And with that, Professor Forbes, I would really invite you to record a lecture on field evaporation theory. I think this would be very, very valuable to not just the PhD students, but to all of us. Mr. De Castro, you have an additional question.
Yes, thank you. So maybe I'm getting something wrong, but you mentioned that there were some groups that were using non-focused lasers, so with a millimeter diameter, for example.
Well, they still are.
So does that imply that there's a larger area being heaten, so to higher temperatures, or not? Or am I getting something wrong?
No, there's definitely a larger area illuminated, but as you can see here, you know, what is actually really mostly relevant is this absorption maximum, which comes from the fact that our atom probe sample is kind of like a small antenna. Yeah? So the heating will be concentrated somewhere close to the tip in any case. Yeah? Even, it doesn't matter if you have a 50 micron spot or a millimeter spot or a 5 millimeter spot. Yeah? The question is, does your laser provide you with enough flux of ions, you know, to spread them over a millimeter and still have enough power close to the tip to trigger the field evaporation?
Okay.
And for infrared lasers, this is usually pretty well doable. But if you want to have shorter wavelengths, we usually have up conversion, yeah, and we lose a lot of power during those up conversion processes, yeah, and so you're kind of forced to focus a little bit more here. Yeah? So typically, I think the guys in Stuttgart use about 50 micron spot size. Yeah, at 50 micron, you still, you know, any vibrations don't matter as much, and alignment doesn't matter as much. Yeah? If you have 1 millimeter, you know, then vibration and alignment don't matter at all. But one of the reasons why we have precise alignment in the commercial atom probes and the Chemica atom probes is because the spot is very small, and then you need to have relatively precise alignment.
Yeah, I was thinking mostly about thermally activated phenomena, but I think in this scale that's not so important, right?
What do you mean by thermal activated phenomena?
Diffusion or phase transformations.
Well, if you heat your specimen enough, that can actually happen. Well,
yeah.
Diffusion does happen on the tip surface. Yeah, that's very well established. That's maybe something I should have also integrated, because if you have an atom that's absorbed on the surface, it can be polarized. It will be polarized because you have field gradients on the surface. Simply because, you know, certain crystallographic facets have different evaporation fields than others. Then on top of that, you have different phases in there which also have different evaporation fields. So this all leads to field gradients on the surface. And because adsorbed atoms always can be polarized, they will move in a field gradient as well. And this enhances the diffusion on the tip. And this is also why we want to keep the temperature as low as possible. There's actually only one example where it's the opposite, and that is the diffusion of hydrogen on tips. There's actually papers from the 70s and 80s where people have shown that on tips, if you have hydrogen, then the diffusion gets worse if you go to lower temperatures, because the quantum mechanical delocalization of the hydrogen atom becomes large enough so that it can tunnel to neighboring sites. But this is the only exception. Everything else is too heavy for that to happen. Would be interesting to do that with deuterium and regular protium, though. Okay, so this was just an introduction. Obviously, there's much more to that, and I've noticed field-induced diffusion I should probably include in the next time as well. Okay, but with that, I think we can conclude it for this session, and can all have a lunch, and I'll see you back at, I think, when do we start again? When do we start again? At 13:30 with atom probe instrumentation. So right now I showed you everything that we think we know is happening, and then you're going to learn about why we know that, and what the limitations of our instrumentation are, and also some operational aspects that so that you know why you should be nice to your atom probe and not, you know, and not cough into the vacuum chamber and do things like that. All right, so have a nice lunch, and I'll see you in, well, about 40 minutes then.